Okay, so as we will start with our discussion, if you remember correctly, we did start or stop last time with me introducing to you the language of binary operation. Okay, we have language of binary operation. Now this time, we will just continue with our discussion about the language of binary operation. As I have written last time that we first define binary operation to be or a binary operation in G, where G here is a function that assigns each ordered pair of elements of G symbolically, that is A star B equals G for all A, B, C element of G. So a binary operation is simply an operation that is imposed or applied to uh, the members of a given set G. Okay? So there is a given set. That's why we started our discussion last time. We defined what set is. It's a collection of well-defined objects. Now, in this case, we talk about language of binary operation. We're referring to simply we have a set G, and then there is an operation assigned to the elements of G in set G, and then that operation, as it was or it is applied to set G, then that operation is called the binary operation. Okay. Now, this time, we will tackle or at least talk about the so-called group. What is group? Now, in math, of course, you've heard already the term group, but I'm not sure if you have heard already the term group under the mathematical definition or discussion. So, when do we say that uh, a set is a group? Okay, take note. Group here is a set. So, we are gonna define now what group is, or when do we have a group in the discussion of binary operation. Now, take note, a group is a set of elements, so it means to say it's a set collection still of well-defined objects with one operation that satisfies the following property. Now, these are the things that we're going to look into. When do we say that a set here is a group? So when you have a collection of well-defined objects, we would then consider that set to be a group if it satisfies the four properties that we will discuss later on. But I'd just like to remind once again that just to reiterate what a binary operation is, a binary operation is defined to be A star B equals G. That is for all A, B, C element of G. So the meaning of this one here, the asterisk here is a general term or general um, representation of any operation imposed the elements found in G. And that operation used there in G is called the binary operation. Now, we will talk about what group is. So when we talk about group, it's simply a set. Okay? It's simply the G here. Now, the moment we apply a binary operation to the group G, and if it satisfies the four properties that we will discuss now, then that indeed would make that set G as a group. But if it doesn't qualify the four or it doesn't satisfy the four properties, then that set is just an ordinary set and can never be considered as a group. Okay? So, what are these four properties? Okay. In other words, by the way, we would write the notation this way. We have G, and then we have, I don't know how to draw this. G asterisk. Okay. Whenever you have this notation or encounter this notation, it means to say G here, being a set, is called a group under a specified binary operation. So this is the general notation. But in this case here, the asterisk can be later replaced with whatever operations you're going to use, maybe multiplication, uh, division, addition. But take note, we're not only limited to four basic because the four operations we know, they are the basic operations like the addition, multiplication, division, and multiplication. But we are not only limited to these operations. There are still other operations that we can do. It's just simply anything that we are going to do or perform within the elements of that given set. And that, as we apply the operation to the elements of that given set, and as it satisfies the four properties, then we call that set now as a group. Okay? Under that particular operation. So again, we are going to specify the operation, the binary operations we're going to apply on that given set, and then we will test whether all the four properties will be satisfied. And that is so, we can already conclude that that group or that set rather is a group under a specific binary operation, whatever operation is that. Okay, so we're not going to take that long, and we will take note of what are these four properties. The first properties is the so-called okay, the four properties. We have the closure property. Okay, what is closure property? Accordingly, this is at least the first or at least one of the four properties that a set should satisfy under a binary operation for that set to be called a group. If any two elements are combined using the operation, okay, using the binary operations, and then if you're going to combine two elements in that set under the specified binary operation, we consider closure property being satisfied if the result must be an element of that set. Meaning to say, if I'm going to impose, for example, the elements in set G, if I'm going to apply now the binary operation specified for that set, and if the result after imposing that operation on the given set, the members of the elements of that given set, and then the result is still on that set, that means to say that set satisfies the closure property, the first property that we need to satisfy. So by symbol, this is how we do it. Okay, I'll just put this in arrow. Please do not be confused with arrow, because arrow actually implies it's an implication symbol, mathematically speaking. But the arrow here is just nothing but just an arrow, just implying that this is the equivalent of the closure property. Okay, do not be confused, because arrow has a meaning in a mathematical discussion, which is an implication. So that is also under logic. But this time, the arrow here is just merely just an arrow. I'm going to imply what closure property is. Okay, so we have A asterisk B equals C element of G. That is for all A, B, C element of G. Sorry, I think I need to write it all together because it looks confusing. We have A asterisk B equals C element of G. That is for all A, B, C element of G. Okay, that is its meaning. Now let's understand this one. By the way, we read this one as A asterisk B equals C. That is for all G. I mean the element of G. That is for all ABC. ABC is element of G. The meaning of this one under the closure property is the one that I explained earlier. Meaning to say, for example, if I have a given set, set G, for example, that's the name of my set. Now, if I'm going to apply the identified binary operations to any elements on G, if the result is still on G, then that means to say that set is closed under that specified binary operation. I'll just walk you through first all the four properties, and then later we will have a specific example, okay? But at least I have explained to you already what a binary operation, or at least what is closure property, how it is being satisfied. By the way, we would then say that the set is closed under the binary operation. We would say that if this property will be satisfied. Number two, the second property we have is the so-called associative property. Associative property. And what is this associative property? Now, from the word association, I'm not sure if you heard this property already, but under the basic discussion for operation, there is what we call uh, associative property of addition and associative property for multiplication. Meaning to say, changing the operation, changing the order of your uh, changing the order on a given operation does not change the result. Okay? So symbolically, we can write this one, the associative property, as like this: A asterisk B asterisk C is equal to A asterisk B asterisk C, comma, that is for all A, B, C element of G. Now, again, we will read this notation here as um, A asterisk B asterisk C is equal to A asterisk B asterisk C. That is for all A, B, C element of G. So the meaning of this one is that if you change the association under the association of the elements of a given set under a particular binary operation, does not change the result. You would still then have the same result. Then, with that saying, the set is said to be uh, associative property holds under that binary operations for the given set. Okay, that's the second. Then we have the third one. Oh, okay. For the third property, we have the so-called identity property. You know, this is one of my favorite topic here for Math 101. The language of binary operation is just, it simply amazes me. Okay, there exists, okay, according to identity property, this is how the identity property is explained. There exists an element E in G such that for all A element of G, A asterisk E is equal to A asterisk A. So symbolically, this is how we're going to write this one, such that for all A element of G, A asterisk E is equal to E asterisk A. Okay? Now, this is what the identity property is telling us. There exists E. E here is the arbitrary element represented by, as known as the identity element present in that given set under that binary operation. So it implies now that if any number or any member of that set will be operated under the given specified binary operation, if it would result to itself, and that element that was operated along with that identified element is the identity element under the binary operation, then that means the same. Identity property was then satisfied uh, under that binary operations for the given set. Later, this will make more sense when we will have the example. Now, the last property is the inverse property. Okay, what is inverse property? For all A element of G, there is an element of A inverse of G such that A asterisk A inverse is equal to A inverse asterisk A equals E. For all A element of G, there exists A inverse element of G such that A asterisk A inverse is equal to A inverse asterisk A equals E. So accordingly, the inverse property goes like this. For all A, that means to say for every elements on that set, there exists its inverse, its opposite, that also exists on that the same set, such that whenever you operate the element in its inverse, the result is the identity element, which is identified number 3. Okay? So far, these are the 4 properties that one set should satisfy in order for that set to be considered as a group. Now, mathematically speaking, group in math is defined to be a set that satisfies the four properties such as closure property, associative property, identity property, and inverse property for that to be or for it to be considered as a group. This is read as there exists, while this one read as for all or for every. And then the ST here stands for such that, which is equivalent also to the symbol like this. Remember the symbol when we have the writing of sets, elements of sets in descriptive form. We use the symbol. This is also read as or read as such that. Anyway, let's have our first example. Great. This is our question. Is a set of non-negative integers under addition is a group, or at least in simple way, we write it this way: G and then plus. This is what we want to find out. Whether G here defined to be a set of a non-negative integers group under binary operation addition. So our set is non-negative integers, and then our binary operation is addition. We would like to find out now whether this is true. By the way, this notation is written whenever G here under this binary operation satisfies the four properties. Now let's take a look to this example. First is we investigate. The first property that we need to satisfy is that um, for all elements A, B, C, let's take a look at this example. When you say G here defined to be a non-negative integers, what are the elements of G? We know that G here has an element of non-negative integers, so that means to say the elements of G is A such that A is an element of Z plus. Now, this is how we define our A. Our G, the elements of G are all numbers that are non-negatives or simply members of the Z plus or Z plus. The meaning of the symbol is positive integers, which are actually what we're investigating here. Now, the question here is that is G here closed under addition? So that's what we need to do. So we're going to investigate now. Let's have, actually, in doing a proving for cases like this, it is easier to prove it by contradiction. Contradiction simply means that you're going to nullify. When I say nullify, meaning to say you're going to disprove the claim by simply providing a counterexample. Counterexample is simply providing an instance under such condition in such a way that will not satisfy the whole case. So with that, we can already rest the case that it's not true. Because remember here, our case is that for all ABCs, according to our definition last time or earlier when what I brought here, that is for all ABCs. So meaning to say that's for all the elements under investigation. But if we can provide one example or one element under investigation that will not go along with whatever the closure property demands, then that means to say closure property will not or was not satisfied. Enough to say that the set here G is not a group under addition. I just like to do a recap from the top. We are trying to prove here whether G as I assigned a variable. Actually, this is just a name of the set. Do not be confused. G, you can use any letter, capital letter, as to represent our set defined to be this one. Okay, our G here, being a set, has a member of A, which is defined to be Z plus. So what are the Z plus? That includes 1, 2, 3 positive integers. Okay? Numbers that are non-decimals or simply whole numbers. Except 0 because 0 is not neither positive nor negative. So it's neutral. So we are going to include it. So we will start with at least 1. 1, 2, 3. Those were the members of our G. Now we're investigating here whether G is a group. As defined earlier what group is, we're trying to find out now whether G is a group under addition. So addition here is our binary operation. So it's addition now that we are going to impose or apply to the elements of G which are 1, 2, 3, 4, so on and so forth, whether G will satisfy all the properties under this addition, under this binary operation addition. Okay, so a group is a set that satisfies the four properties. Okay, next in this problem, we're trying to test now whether set G here is a group under a binary operation addition. So this is now the operation that we are going to apply to the members of G to check whether the four properties will be satisfied. What I'm saying earlier is that in cases, there is what we call in proving that to prove or to disprove the claim, we provide counterexample. We call it proving by contradiction. We're not doing here a formal proof, but rather we're just making here a walkthrough on how things will be done. So what we're going to do here to prove whether closure property is satisfied by group G here, we will provide a counter example, or at least we will disprove it. In that case, we will disprove it using counter example. What I'm saying is that considering the members of G, if I can provide one example that do not satisfy closure property, it's enough already to say that the set G here is not a group. Because according to the definition earlier, that is for all ABCs, element of G. So that is for all elements of G, for every element. But if I can provide one example, which is a member of G, but does not satisfy the closure property, then we're good. Meaning to say, I can already conclude that G here is not a group because there is at least one example or one element of G that do not satisfy the closure property, which is one of the four properties that G must satisfy for G to be considered as group. Now, what I'm saying here is that if I can provide a counterexample, then I'm going to use that one to nullify my claim that G here is a group. But if I can provide one, at least for the purpose of discussion here, I'll just provide two, at least two instances that G here wouldn't satisfy closure property. Under this set here, I can pick elements 1 plus 2. 1 and 2 here are members of G, right? Because 1 and 2 here are Z plus. They are both positive integer. The answer here is 3. And take note, 3 is also still a Z plus, which is a member of G. Thus, with this example, at least I can provide you that indeed it's close. Another one, if I have 5 plus 7, 5 and 7 are both integers, positive integers, so that is a Z plus number. So, the result of this is 12. And still, 12 is a member of G. For 12 is still a Z plus. So with that saying, I can say now that at least with this few example, the group or the set rather, the set or G is closed. G is, I will just write it here. Therefore, G is closed under, okay, under addition. So I'm saying here that G here is closed under addition, meaning to say set G satisfies the closure property. Because any positive integers added to another positive integers, the result is still a positive integers. There's no way you're going to add addition, or you're going to have positive integer plus positive integer. The result is decimal. That's not possible. And there's no way also that integer, positive integer plus positive integer, the result is negative. There's no way such. So that's why I didn't say I didn't say that G here is closed under addition. Because for every positive integer added to a positive integer, the result is still a positive integer. Thus, G is closed. Property 1 is satisfied. Now, let's move to the second property. The second property is, in associative property, this is how it works. Like 1 plus 2 plus 3 is just equal to 1 plus 2 plus 3. 1 plus 2, this is 3 plus 6. This is still 6. Thus, changing the association now, still don't matter or does not change the result. So thus, associativity holds. Okay, therefore, associativity holds for G. Okay? Meaning to say associativity holds for set G. Okay, at least G now here satisfy two. We still have two more properties to satisfy. But mind you, in the process of writing or at least in the process of investigating, if set or property one was then not satisfied, you don't need to proceed to the last. You can just easily stop there and say that G is not a group because at least it fails to satisfy the first or the first property you have tested. Okay, but in our case, I would like to complete the four for the purpose of discussion. But in your real investigation, investigating whether G here is a group, if the first property was not satisfied, you can already stop and say that G is not a group because it fails to satisfy one property. Remember, we have to satisfy all the four. So if it cannot satisfy one, then that's enough to say that it's not a group. Okay, let's have three. The third property is the identity property. Sorry. I just need you to understand that what is identity property? According to our definition, identity is there exists an element E in G, meaning to say there must be an element of Z plus here such that A, any element of that set, operated with your given binary operation, in this case addition, the result is still itself. So for example, but first thing that you need to do is identify first what is the identity element. What is the identity element of G? The G here is referring to Z plus. Okay, what is the identity element of G under addition? Under addition. Okay, so under addition, we know that the identity element for addition, what number or at least element you can add such that, what number you know that once added to any number would give you the same number. We have any number added to zero is the same number, correct? That's the point. Because the identity element for addition is zero. The question is zero a member of Z plus? No, because zero is neither positive nor negative. So with that saying, property number three is not or was not satisfied by G because the identity element for G under addition is I don't know. What is the identity element? This is not correct. What is the identity element under addition? So, what is the identity element under addition? The answer is zero. The question here is zero element of G, where the G here is this set. That's the question. The answer is no, right? Because zero is not a positive integer. It's neither nor positive. So with us saying G here, G fails to satisfy or failed to satisfy identity property. Identity property. Thus, G is not a group. So with that saying now, you can say that G is not a group because it does not bear the identity element, or at least the identity property was not satisfied by G. I don't know. This is also what I am confused the book because in this book the discussion included zero as members of the positive integer, non-negative. But for my assessment, we cannot include zero as members of Z plus. It's because or non-negative integers. It's because zero is neither positive nor negative. It's neutral. So you cannot carry it over as positive as much as you cannot carry it over also as negative. It's the boundary. That's why I don't know in this discussion because the book here says that does it also satisfy the identity property, but I don't think so it is. Because our discussion here is not negative and zero is not considered as non-negative number. It's neither nor. So that's why, as for me, assessing it, three here is not satisfied. The book here says it was satisfied, which I don't agree. I don't know. I don't know with this book what it says. Anyway, just for the purpose of continuing this one, let's have the fourth property. But again, it's already sufficient up until number three. It's sufficient to say already that G here is not a group because it fails to satisfy the property number three. But since we are doing this for discussion's sake, I'm going to continue with number four. The fourth property is inverse property. According to inverse property, for every or for every A or for every element in G, okay, for every element in G, there must be an A inverse. For every A element of G, there must be an A inverse, which must be an element of G such that A asterisk A inverse is equal to A inverse asterisk A equals E. That is the explanation. Now, in this case, let's have this one. We can actually say that, for example, 1. What is the opposite of 1? Positive 1. Okay, we have negative 1. So we'll say that 1 plus negative 1 equals 0, right? 1 plus negative 1. The element 1 here, the element 1 here is an element of G. The inverse of 1 is negative 1. So 1, our operation is addition. So 1 plus negative 1, the answer is 0, which is supposed the identity element for addition. Okay, we can have here another that 2 plus, what is the inverse of 2? Negative 2. The answer is 0. Actually, we got the identity element for addition. The problem here, the condition as was said that the result of doing this one must still be an element of G. The problem here, 0 is not an element of G. So from there, fourth property was not satisfied. Also, negative 1 here, negative 2, as these two examples are showing us, they are not members of G because negative 1 and 2 are non-negative. I mean, they are negative. They don't belong to the non-negative group. So with that saying, G do not possess the inverse, at least the inverses of each elements. So the elements of G are 1, 2, 3 to infinity, do not possess their inverse, the inverse of G. The symbol A inverse is the opposite or the inverse of the elements of G. If the element of G is 1, the inverse of 1 is negative 1. Such that negative 1 here is not a member of G. With that saying, you know that fourth property was not satisfied. So with that now, all in all, we will say that G, this one, is not a group under addition. I will not circle this because you might be thinking that it's a circle class. Period. Okay? A, G under a binary operation addition is not a group. G is not a group under a binary operation addition because it fails to satisfy inverse property as much as. By the way, this is what we call now a counterexample. Counterexample is simply providing at least one example that do not go along with what is claimed. Then that's sufficient already to say that that claim is, that claim can be nullified already by just one mere example. We call that as counterexample. But you have also to consider that that's not the case all the time. This is so in this case, it's because there is what we call now we claim that for every element of G. That's why if I can provide an element of G that do not go along with this claim, then that means to say it is sufficient already to nullify the claim. Okay, that is called proving by contradiction. I'll prove you wrong by providing you one instance. That is contradiction, proving by contradiction. Let's have set A here, containing 2, 1, 0, -1, -2. This is my set. Let's see whether A here is A group under multiplication. Let's investigate. Okay? So we have here set A containing elements 1, 2, 0, -1, -2. Let's find out now whether A here is a group under multiplication. This is multiplication. Now let's investigate now. First property is A closed, meaning to say that the members of A, once added or once multiplied, applying the operation multiplication, is the result still in A? That's the question. So let's investigate. 2 plus 0. 2 and 0 are members of A, correct? The answer is 2, which is still a member of A. So it's close under this example. Multiplication. Times 2 times 0 is 0. So which is still a member of A. So it's close. Another instance. -1 times -2. The answer is +2, correct? Which is still a member of A. So it's close under these two circumstances or circumstances. Now let's provide one example.
Sir,
Yes.
can you multiply the element by itself or delay?
You mean to say 2 times 2? Ah, yeah, that's a good question also. I haven't considered that. Because, yeah, I think that is one of the trivial case here. You have 2 times 2 is equal to 4. 2 here is an element of element of the set. And then 2 here is another element of the set. I think it's not. If I'm going to stick with the definition, it says there that A, binary operation B. It doesn't say there that A, binary operation A is the case. It must be, it's not allowed, we're not supposed to have A times A, but rather A times B, A times C. To another, it must be multiplied to another members of the set, but not to itself. So we are not supposed to answer that question, at least we're not going to perform the binary operation to a members of the set to itself, but rather to other members, operated to other members of the set. Unless if in the description or instruction, you are going to identify the property first. But since it wasn't mentioned, we are not supposed to do it. Okay? But that's a good observation. Any other thing? So, do you think that A here is close under multiplication? That any number, members of the set here, multiplied to another members of the set, the answer is still on the set. Okay, because if you have 0 times -1, the answer is 0. Still 0 is a member of the set. So let's say this is A is closed. Okay, closed because it satisfies the closure property. Let's have the second property. Third property is associative property. So you have 2 plus 1 plus 0 is it equal to 2 plus negative or plus 1 plus 0? Is it true? Okay, this is true. So at least the associativity holds, correct? By the way, more or less it's like this. In terms of associativity, real number, one of the properties of real number is associative property. That's one of the properties of real number. And these numbers are real numbers. So thus it's like if my father is real number, then more or less I inhibit the properties of my father, which is associativity. So no wonder that associativity is more likely will be carried over because it's just like what my father has, more or less I'm going to inherit it being a son, something like that. That's the idea. So since these numbers here are also real numbers, thus more or less the associativity holds for these numbers as well. Because real numbers, one of the properties of real number is associativity. Associativity equals. Now let's have number 3. What is the identity element under multiplication? One is the identity element in multiplication. Okay? So 1 is the identity element in multiplication. Okay? And 1 here is one element of A. Because according to this, there exists an element E in G such that for all A and G, A asterisk E is equal to E asterisk A. So, do we have it? Yes, we do have it. Let's investigate. Accordingly, such that the identity element under the binary operation applied to other elements, the result is itself. So if we have 2 multiplied to 1, the result is 2. That means to say it was satisfied. And then when you have 1 multiplied to 1, the result is still 1. 0 times 1, the result is 0 itself. Negative 1 times positive 1, the result is negative 1. So still, it was satisfied. Because accordingly to the to recall, we all know that it says that the set must contain the identity element such that A asterisk E here is the identity element, which is in our example is 1, is equal to E asterisk A. So it's like, if I will give you an example, 1 or rather 2 times 1, 1 here is your identity element. It's just equal to 1 times 2 equals to 2. 1 times 1 is just equal to 1 times 2, which is equal to 2. Can you think of any element here that once operated under multiplication to our identity element 1 will not give you itself? If we have such, then we can nullify this. But if we cannot provide 1, then we're good to go. So between 1, 2, 0, negative 1, negative 2, any, like if we pick 1, 1 times 1 is equal to 1 times 1 equals 1. So, satisfied. If it is 0, 0 times 1 is equal to 0 times 1, sorry, 1 times 0 is equal to 0 itself. So, it's satisfied. Negative 1 times positive 1 is just the same with positive 1 times negative 1, that is still negative 1, satisfied. If we will have the negative 2, the same is true. So indeed, property number 3 is satisfied. Okay, what about number 4? What do you think? Is property number 4 will be satisfied? For our element 2, what is the inverse of 2? Negative 2. Is negative 2 a member of A? Yes. Correct? It's there. And then 1, what is the inverse of 0? Actually, I'm not pretty sure though, but I don't think so 0 has an inverse. Because the inverse is actually, for at least for multiplication, that is, the inverse of 0 is 0 times its reverse. Because if you have 1, the inverse of 1 is, sorry, I think the inverse is not present. I'm making stories. What's the inverse of 2 under multiplication?
Negative 2, sir.
That is for addition. But for multiplication, the inverse of 2 is 1/2. Because once multiplied, the answer is 1. Take note, the result must be identity. That's why our definition last time is A asterisk A. Remember this one, A asterisk A inverse is equal to A inverse asterisk A equals E, the identity element. The identity element is 1. Therefore, if you have 2 times negative 2 here, as claiming that 2 here is the inverse of 2, the answer is negative 4, not the identity element. Therefore, it clearly says that negative 2 is not the inverse, but 1/2 is the inverse of 2 under multiplication. The inverse of 2 under multiplication is 1/2. And in this case, so we have 2 then times 1/2 as the inverse of 2 is 1. Yes, it's satisfied, but the problem here, 1/2 is not an element of A, correct? Thus, A failed to satisfy what property? Inverse property. Inverse property. Hence, A is not a group. There's continuation. A is not a group under multiplication. So in this situation here, we can conclude that set A, this set, is not a group under multiplication. Yes, it satisfies the first three properties, but it fails to satisfy satisfies the last property, which is the inverse property. Thus, still A here is not a group, for it did not possess the inverse, or the inverses of each element. They were non-members, or they are not members of A. Thus, property number four is not satisfied. Do you think this set here is a group under addition? Okay, let's try this one, showing you. Okay, we're good with this one. That A here, set A is not a group under multiplication because it fails to satisfy inverse property. Yes, the first three properties were satisfied, but the last one, it fails to satisfy. That's why it's not a group. Now let's investigate whether this group is a set, or this set is a group under addition. Let's find out. Let's change our operation to addition. First question, is it closed? Now this is what I'm telling you. Counter example. Counter example. It's like counter attack. You attack it the opposite way. If you can provide one, then it's enough to say that it's not closed. So example, if I can provide one instance that adding two members and adding or applying addition to two members of the set, the result is outside the set, then that's enough to say that it's not closed. Example, 2 plus 1. 2 plus 1, 2 and 1 are both members of A. Under the binary operation addition, the result is 3. But 3 here, since 3 is not an element of A, thus A is not closed. So you're enough to say, therefore, A is not a group under addition. That's it. Since see, this is now an example of a count. This is now this is what I'm telling you earlier, the so-called counter example. I'll provide you one instance that will nullify it, such that enough to say already that it's not true. So we know that 1 and 2 and 1 here are members of A, but as binary operation addition was applied to 2 and 3 being members of A, the result is 3. And since 3 isn't a member of A, thus it fails to, thus the set fails to satisfy the closure property. As shortly say, we say that A is not closed. Therefore, it's already sufficient to say that the set is not